All right, so hopefully water, I mean, you see water being asked to do a lot. It's obviously a pretty common molecule that we're familiar with. So water, again, oxygen has 1, 2, 3, 4, 5, 6 valence electrons. Now I'm going to see this loner electron. I'm going to line one of my hydrogens up with it. Hydrogen has 1 valence electron, and then I will form a bond here. Okay, and then SO2 is a little bit harder. 1, 2, 3, 4, 5, 6. Sulfur has 6 valence electrons. Now oxygen, I'm going to line the oxygens up. Now this one's tricky. 1, 2, 3, 4, 5, 6. Bond. 1, 2, 3, 4, 5, 6. Bond. Now, ooh, I shouldn't have given you this one. It's okay. All right, so we're trying to find bond polarity, meaning is there even or uneven sharing in the bond? Now remember, even sharing is called non-polar. Uneven sharing, meaning one is more electronegative than the other, is called polar. So what we're going to do is we're going to look up their electronegativities. So you find oxygen. I'm pretty sure oxygen is 3.5 on your electronegativity chart. And hydrogen, I think, is 2.1. And you subtract them, right? It's called the change or difference in electronegativity. So 3.5 minus 2.1 is what? 1.4? And I know I gave you that this is kind of messed up, but the 1 point, so this cutoff right here is 1.7, and this cutoff right here I think is 0.8. It's actually different on different charts, so just follow whatever the chart says. Either way, 1.4 falls in the polar covalent. Okay, so this is a polar covalent bond right here. That's a polar covalent bond. This is a polar covalent bond. It's the same bond. It's oxygen and hydrogen. So it's the same type. It's polar covalent, meaning there is uneven sharing. Here's why. Oxygen is really, really, really electronegative. So these 2 electrons, the oxygen's going to be like, yeah, I'm a lot more attracted to the electrons. So I'm going to yank the electrons closer to myself. Okay. Now, something that's going to be new or newer is when that does that, they form what are called, dipoles. And the dipoles are going to be these arrows that we draw, and we point them to the more electronegative element. Okay? So the hydrogen is less electronegative than the oxygen, so I draw the arrow and point it at the oxygen. And then I do it again for this bond. I draw the arrow and I point it at the oxygen. Okay, so now this is going to be something new. Now what this means is that if the electrons are existing closer to the oxygen, well, electrons are negatively charged. So this end of my dipole or my arrow becomes, this is it's a Greek symbol, it means slightly negative. And this one is slightly positive. Now remember, so that kind of looks like a plus sign, okay? Slightly positive and slightly negative, meaning this region over here is closer to where the electrons are hanging out, and this region over here is closer to where the electrons are being pulled away from. So because electrons are negative, this area becomes more negative, not completely negative, but slightly negative, and this area becomes slightly positive. Now the same here. The oxygen is yanking really hard on those electrons. So this area of the arrow becomes slightly negative, and this arrow becomes slightly positive. It like looks like an S with a tail, pretty much. Okay, it means partial. So this means partial, partially positive, partially negative. Okay, or it's like an unfinished 8 if you want to look at that. Okay, So again, these arrows are called dipoles. It's showing the uneven sharing of electrons in the bonds. And again, this happens when an atom within the bond is more attracted to the electrons. It's like, so in this bond right here, oxygen is like the sumo wrestler. It's pulling way harder on the electrons than hydrogen is. So the electrons actually live or exist closer to the oxygen atom than they do the hydrogen atom. They don't share them evenly. Now, why don't these become full positive and full negative? Well, neither one of these atoms, hydrogen or oxygen, is strong enough to completely remove or lose the electron. So that if that happened, those would be ionic compounds. That's not what we're doing. We're doing covalent compounds or molecular compounds that are forced to share because neither of them is strong enough to rip one and lose one from electron, but they don't always share evenly. It isn't always an even sharing. Okay. All right. So now I'm going to go back to the slides. So SO2, now, sorry. Well, my mouse is going crazy. So SO2, I'm not going to have you actually understand this Lewis structure. It's actually a little bit challenging. I'll go back to my whiteboard. You don't need to know this. I just want you to watch what happens. SO2 is weird because nothing is stable once you bond everything once, so you're forced to split up a lone pair of electrons. And specifically what happens is this electron right here and this electron right here form a multiple bond. Oh, wait, why is it doing that? So you get a multiple bond here. And then what's even crazier is that this little electron right here ends up going over here to complete the octet. So I don't need you to know that. This one is more complicated. The reason that is because I know that we draw the electrons and give them to the element. Like we say sulfur has 6 valence electrons, but it has 6 valence electrons for anybody in the molecule to achieve an octet. They all can be shared however you want. Now, I don't need you to know how to do this, but I do need you to kind of see that that can happen. Just because I give 6 electrons to sulfur based on the periodic table doesn't mean they have to stay with sulfur. They will do whatever it takes to be stable, and that means completing an octet. And if that means an electron finds its way over to another atom to achieve stability, it will do that. So look at 2, 4, 6, 8 electrons around oxygen, 2, 4, 6, 8 electrons around sulfur, 2, 4, 6, 8, or sorry, 2, 4, 6, 8 electrons around oxygen. So this is stable. Now, in terms of polarity, we're going to draw a dipole. Now, your dipole gets pointed towards the more electronegative element. So that's going to be oxygen, right? Oxygen is the second most electronegative element there is on the periodic table. So that's a dipole. Then sulfur, oxygen. Oxygen is the second most. So again, there is a sumo wrestler in here, right? There is an atom that is more attracted to electrons. It's oxygen. So yes, they share them, but they don't share them evenly. Oxygen's going to pull really hard on these electrons. So you look up on your electronegativity chart, which I gave you. Let's see if I can go back to my slides. Here it is. So you find sulfur, its electronegativity is 2.5. You find oxygen, its electronegativity is 3.5. And then you subtract them, always making a positive number. You will do it just so that you always get a positive number. So I'm going to do the oxygen, which is 3.5, minus the 2.5. So this is a change in electronegativity. And that's 1. Now, in your chart, where does 1 fall? Well, I know I keep telling you guys the numbers aren't here for the cutoffs, but this is like 0.8 or 0.9 right here, and this is 1.7. So this is a polar covalent bond, meaning uneven sharing, meaning the oxygen is going to very, very strongly attract the electrons and pull it closer to itself. Now, electrons are negatively charged. So if more electrons are living closer to the oxygen, this end of my dipole becomes slightly negative because that's where I'm finding more of the electrons, and this end becomes slightly positive. Again, this end is slightly positive while the electrons are being yanked down, and this end is slightly negative. Okay, so these are now called dipoles. It's these arrows that I'm drawing, a dipole. okay? So again, this is a polar covalent bond. This is a polar covalent bond, and they're the same exact bond. It's a sulfur oxygen. Yes, I realize this is a double bond and this is a single bond, but that doesn't change the electronegativity values of the atoms attached, okay? All right, so we're going to move on because I'm going to skip this. We have to do now what kids tend to find a little bit harder, and that's called molecular polarity. Okay, so right now what we just did is we discussed bond polarity, meaning we said, okay, we looked at two atoms, and then like in our last example, we were looking at sulfur and oxygen. Okay, we were looking at that bond, and we'd said sulfur's electronegativity is 2.5 and oxygen's electronegativity is 3.5, which is a difference of 1, which made this a polar covalent bond. Okay, so now what's going to happen is, in order to determine the polarity of the entire molecule, we have to understand what that's going to have to do with molecular shapes, okay? So two things are going to have to be true for molecular polarity. First thing is you have to look at bond polarity, and then after you look at the polarity of the bonds, you have to determine the shape and what those dipoles in the molecule will do, okay? So remember, we said if there was no big difference in electronegativity, the bond was nonpolar. So the same thing goes for a whole molecule, okay? If there's no overall dipole moment, meaning all dipoles cancel each other out, we now call the entire molecule nonpolar, okay? Now this happens in general to symmetric molecules, and we'll talk about symmetry in a second. Now, if there is an overall dipole, like the dipoles don't cancel out, they call it a net dipole moment, okay? Then the whole entire molecule is called a polar molecule. So the bonds have to be polar, and then the shape has to also be what's considered something to be polar. And those shapes are asymmetrical. Asymmetrical shapes are always polar. Now, again, we're going to talk about symmetry in terms of shape in just a second. So, if you look at this water molecule, okay, you have the dipoles pointing towards oxygen. The dipoles pointing towards oxygen. Water is bent. That is its shape. It has two bonded pairs, so it's A, B, two bonded pairs, and then two lone pairs of electrons on the oxygen. And it's these lone pairs that cause the water molecule to bend, okay? And if you notice these dipoles, they're all going in the same direction. They're all being pulled. All those electrons are all being pulled towards oxygen. So you have a very, very big, strong region of electrons around oxygen, which leaves the hydrogen regions, this hydrogen right here and hydrogen right here, slightly positive. Now, bent is an asymmetrical shape. Okay? Bent is an asymmetrical shape. So because it is asymmetrical, meaning any way you look at it, it's not the same. So like the distance from here to here is not the same as the distance from here to here. Okay, it's not the same any way you look at it. So asymmetrical molecules are always polar. So not only is this a polar bond, this is a polar covalent bond, this is a polar covalent bond, okay? Not only that, but the entire molecule is polar, meaning this whole region of the water molecule is slightly negative, and under here where your hydrogens are, this whole region under here is slightly positive, okay? This is what makes water pretty special, it being polar, and you've probably learned a little bit about this in biology. Water is polar, which gives it some really, really amazing and kind of crazy properties. Water molecules like themselves. They are attracted to themselves. So water molecules stick together. They stick to one another. Okay, so let me see if this is out of order. All right. Okay, I'm gonna go back to my whiteboard. Maybe. All right. So I want to show you what polarity does. Here's water, right? If you draw it, and it has, oh, that was pretty bad. 2 lone pairs of electrons, and then like here's another water molecule, right? And then like here's another water molecule. And I could just draw water molecules all over the place, okay? Lone pair, oops. Well, we just said that the oxygen-hydrogen bond is a polar bond, meaning the oxygen is really attracting those electrons more than the hydrogen in all of these water molecules, right? Because oxygen is very, very electronegative, meaning it is very, very attracted to electrons. So what does that mean? Well, if it's very, very attracted to electrons, the electrons are existing up here more, okay? And then if they're being pulled up here, electrons are partially negative or are negatively charged. So you end up with a partially negative region here. And then under the bottom of the water molecule, this region is slightly positive because the electrons are being pulled away from here. So again, this region is slightly negative in this water molecule, and this region is slightly positive. And this region is slightly negative, and this region is slightly positive. Negative, positive. Well, look at this. If these water molecules get close enough to each other, this negative region of the oxygen and this positive region of another water molecule will attract each other. They don't they don't bond, they just attract each other. This is attraction. So look at this oxygen that's slightly negative and this hydrogen that's slightly positive. They will attract each other. Does anybody remember what this is called? This has a special name. Does anybody remember what it's called? This force of attraction? It's called something bonding for water. Anybody know? Hydrogen bonding. Okay, this is called hydrogen bonding. Now, this can be kind of misleading. They aren't actually bonded. So like this oxygen of this water molecule and this hydrogen of a separate water molecule are not actually bonded together, but they are attracted to each other. This is what causes water molecules to stick to themselves, is this hydrogen bonding force of attraction, because water is polar. This is what causes hydrogen bonding. The fact that a water molecule is polar and there's an entire region of it that is partially negative and another region of a water molecule that's partially positive, and they attract each other, okay? So polarity is what causes hydrogen bonding to happen. Well, is partially what the cause is. Now, water sticks to itself. If you've ever taken a penny in a class and put a bunch of water molecules on it. So like I'll draw like a penny, okay? And then you stack water molecules on it, right? You'll notice that if you do it over time, the water molecules won't just slide off the edge. It kind of like will form a dome on top of the penny before it falls off. That is the water molecules sticking to itself. And by sticking to itself, I mean water molecules are attracted to themselves. They're other water molecules. So they form that kind of dome because they're like, oh, those hydrogen bonds are so strong that they don't want to fall apart. So they're held together, and it'll actually form a dome over the penny before eventually you put too much water and it'll break. It'll break over the penny. But that is a show or an example of you seeing water being polar in action, forming a dome over the penny where it's just like, ooh, I don't want to fall off the penny. I'm going to stick to myself and stick to myself over and over and over again. Again, it's called, in water specifically, it's called hydrogen bonding. And the reason that it happens is because of the bent shape being, this is bent. The shape is bent. bent shape is asymmetrical, meaning it does not look the same every way you look at it, okay? And that's what causes an entire molecule to be polar. Wait a second. Okay, so let's draw, please draw, oops, I'm gonna go back so you can't see that. Let's draw ammonia. Please draw ammonia. So I'll leave this up. I'd like you to take a moment and draw ammonia. Ammonia's formula is NH3. So please draw ammonia. So nitrogen has 5 valence electrons. Hydrogen has 1 bond. I need 3 hydrogens. Okay. So here it is, ammonia. Now, I need you to be very careful. In space, it really looks like this. Okay. Now, so this is A, B3, 3 things bonded to it, and a lone pair of electrons on the central atom. Okay. What shape is this? So I'm going to wait till I hear a shape. Trigonal what? Is it planar or pyramidal? So trigonal isn't enough. Trigonal what? Is it a pyramid or does it lay flat? Well, it is a pyramid. Why? Well, it doesn't lay flat, trigonal, pyramidal, because this lone pair of electrons pushes these bonds down, right? The Vesper theory, valence shell electron pair repulsion. The fact that there's a lone pair of electrons right here causes these bonds to not want to lay flat and move down, okay, into a pyramid. So this is an asymmetrical shape because of that, okay? So look at, you got, technically this is 107.5, this is 107.5, and the backwards is 107.5, and then, so it's hard to see the backwards one, it's right here, okay? And then you got all of this empty space up here, okay? That is not symmetrical. It's different up at the top. There's a lot of empty space, so not symmetrical. Things that are not symmetrical are polar. The whole so this is a polar bond because the nitrogen yanks harder on the electrons. Now, if you notice, that means all of the electrons are being yanked towards the nitrogen. So all of these dipoles are going all to one location, making this end slightly negative and this end slightly positive. So the ammonia is a polar molecule. It has polar covalent bonds, and it is also polar. The whole molecule itself is also polar because all of the dipoles pull together all towards the nitrogen. They don't cancel out. So polar bonds and a polar molecule, meaning ammonia does similarly to what water does. It behaves similarly as water. So what do I mean by that? Well, if ammonia is polar, watch. I just drew 3 different ammonia molecules. Okay? So because ammonia is polar, that makes the nitrogen end slightly negative and the hydrogen ends slightly positive. Slightly negative, slightly positive. Slightly negative, slightly positive. So look at this slightly negative end of the nitrogen atom on this ammonia molecule is going to be attracted to this slightly positive hydrogen end on this ammonia molecule. And this slightly negative nitrogen is going to be attracted to this slightly positive end of the ammonia molecule, okay? And so ammonia does similarly to water that water does. It is polar. And this is also another type of hydrogen bonding. It's a hydrogen being attracted to a nitrogen. Okay, so water is not the only thing capable of hydrogen bonding. Hydrogen bonding, meaning ammonia likes itself too, and it does because it's polar. There is overall uneven sharing or distribution of electrons. I'm gonna change that to distribution. Overall uneven distribution of the electrons. Meaning most of the electrons are hanging out up here next to the nitrogen because the nitrogen's yanking harder on it. Questions? So an important part of this chapter, okay, please draw now carbon dioxide before I move on. Please draw carbon dioxide. Carbon dioxide. CO2. Carbon has 4 valence electrons. Oxygen has 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So I have to bond at least once. And then I notice nothing has 8 electrons around it yet. There's no stability yet. So I'm forced to bond again here. This is alone and this is alone. Now I'm going to redraw this. This is ugly, okay? This is a double bond. So it's C double bond O. And then the lone pairs of electrons on the oxygens. You cannot forget to include those. Okay? So this is an atom in the middle, carbon, bonded twice. Bonded to oxygen, bonded to oxygen. Now, I would like you to go in and include dipoles. Is there an element between carbon and oxygen that yanks harder on the electrons? Absolutely. Oxygen is the second most electronegative element right behind fluorine. So the oxygen is going to pull the electrons closer to itself. Well, that's the same case here, right? What shape is this? This is linear. It's a straight line, okay? So this is considered a symmetrical shape, meaning the distance here and the distance here are the same. A line is a line is a line, all right? It's symmetrical. So what happens? Now, if you have a moment, could you look at me on the computer instead of the screen? Okay, if you can look at me instead of the screen. So you have, right, the carbon in the middle, right? And then the oxygen is like yanking this way. But then the other oxygen is yanking equal and opposite the other direction. So because of that, so if there's a pull this way and then there's a pull this way, equal opposite direction, there is no net, no overall, that's what net means, dipole. Meaning these dipoles cancel each other out. So like one goes this way, but then the other one goes this way. So this molecule is non-polar. It is not polar. There is no uneven sharing overall because both of the dipoles pull equal and opposite directions and they cancel each other out through symmetry. Okay, so they cancel each other out through symmetry. Cancel, so the dipoles cancel, through symmetry. Okay, so we're gonna not fast forward. So really what we need to do is understand what shapes are responsible for what, which shapes are symmetrical and which shapes are not. So a bond is polar when there's a difference in electronegativity between 2 atoms sharing electrons. A molecule is polar when the molecule is not symmetrical and the dipoles don't cancel out. Okay, so this is the answer. Now, I'm going to take you through this flow chart of how you determine bond polarity, and then I'm going to let you go. I'll put your homework up in a little bit. Sorry, I didn't get a chance to put it up. So the first thing you have to ask yourself is if the shape is symmetrical or not. Instantly, if it's an asymmetrical or not symmetrical shape, the molecule's polar, no matter what. The problem is that sometimes you can have symmetrical shapes, and if you throw out a different atom being attached, it can turn the molecule polar, okay? So in the carbon dioxide example, we had both of the atoms were the same thing attached to it. They were both oxygens. So the molecule was nonpolar because the dipoles canceled each other out. However, if I were to do something like this, now this isn't going to be a real Lewis structure, but I just want to show you something. This is not real, okay? I just want to show you an example. If I were to have that carbon oxygen, and then I did this. Actually, this is going to be a real structure. Now, this is linear. This is linear. It's a line, meaning it's a straight line, and linear is symmetrical. However, in the tug of war, oxygen yanks way harder on electrons than sulfur does. See how these are not the same two atoms bonded to the central atom anymore? So while this is a symmetrical shape, the oxygen is going to win this tug of war, making the symmetrical shape actually be polar. Okay, so this would be a polar molecule. Electrons would live closer over here because oxygen is a stronger pull on the electrons than sulfur is. Okay, so sometimes symmetrical shapes can be polar, is what I'm trying to emphasize. Okay, so then we got to go through all of our shapes. Ready? Oops. So, oh wait, where's my, oh no, it's missing. Okay, so ready? I'm going to give you these and then I'm going to let you go. We have all of the different shapes, assuming that everything is attached to it. So symmetrical shapes, and we'll talk more about this tomorrow. Symmetrical shapes mean nonpolar most of the time. Okay, here they are. Linear, trigonal planar, tetrahedral, octahedral. Sorry, I know you need to leave. So octahedral, and then trigonal bipyramidal. Bent, asymmetrical are bent, and and trigonal pyramidal. Polar. Okay, so your homework tonight is going to be based on that. You guys can go ahead and head out. Sorry, I know I went a little bit over. I will post these notes later.